What's up everybody? Mr. Gill here, back with another video, this time for chapter 7, which is going to talk about method 4. We've already seen 3 methods, and this will be the 4th method to find the enthalpy change of a chemical reaction, and it's called Hess's Law. Now before we start, there are 2 things I need to remind you of. Number 1 is from chapter 5, where we saw that if we reverse the reaction, the enthalpy change switch signs. And the example is right here. You've got A plus 3B going to 3D plus C with an enthalpy change of positive 25 kilojoules. If you were to flip the reaction around, the enthalpy change would become negative 25 kilojoules. Secondly, we saw this in chapter 4 when we used the ratios, the stoichiometry. We saw that if we multiplied or divided a chemical reaction by a specific constant, then the enthalpy change would also get multiplied or divided by a specific constant. So like in this example here, notice how the chemical equation is being multiplied by 3. If the chemical equation is being multiplied by 3, then the enthalpy change is also being multiplied by 3. And you can see how the enthalpy change has just tripled. Same thing for this example here. Notice how we are dividing our reaction by 2. We divide our reaction by 2, and the enthalpy change gets divided by 2. So these are the things that we've already seen in chapter 5 and chapter 4, which we'll use for Hess's Law. So Hess's Law, basically what it is that it's another method to determine the enthalpy change if you're too lazy to do molar heat experiments, or if you don't have access to, let's say, bond energies. Hess's Law basically uses simpler chemical reactions with, if you already know their data, you know their enthalpy change, and what you do is you combine the reactions together, you add them to get to the reaction that you want, which will get you the enthalpy change. Now before we start, 2 key points. Key point number 1 is that when you add chemical reactions together, what you'll see is that compounds will cross out. Compounds will cross out only if they are on the opposite side of the arrow. So for example, notice that 2C on the top reaction is on the right side of the arrow, and 2C on the left side of the arrow, 2C on the second chemical equation is on the left side of the arrow. So since they're on opposite sides, they will just cross off. Now states do matter here, so if the states are not the same, then you can't cross them out. So if the C's has, in the example we just talked about, had different states, then they would not be able to cross out. They must have the same state. Okay, so we can do this now. Let's see the method, and you'll see that it's actually not that bad. Okay, so you're given 3 chemical reactions, all of which you know the enthalpy change for, but your job is to try to find the enthalpy change of the desired reaction. So the way you start is you take a look at your desired reaction, and you try to find a compound in your desired reaction that only appears in one of the 3 chemical equations that you're given. So let's have a look at C2H4. Is C2H4 in only one of the 3 chemical reactions that are given? Absolutely. It's in the first one only. So now what we do is we got to manipulate the first equation by either flipping it or multiplying by a constant so that the coefficient matches to the one in our desired reaction, and of course we hope that it's on the same side as well as our desired reaction. So in our desired reaction, C2H4 is on the left side of the arrow, and it has a coefficient of 1. If we look at the C2H4 in the top reaction there, it is also on the left side of the reaction. So that's good. We don't need to do anything about that. Also, the coefficient is also 1. So that means that we actually have to do absolutely nothing. We're actually happy with this. Now that we know the C2H4 is in the right place and it has the proper coefficient in front, I put a check mark next to it. I put the check mark next to it, and what that means is that this equation number 1 up there, is locked. We cannot manipulate it because C2H4 appears only once there, and we've confirmed that C2H4 is in the proper location and has the right coefficient in front. So what do we do next then? Well, what we're going to do is we are going to now do the same process. We're going to do step 1 and step 2 again. We're going to look through our desired reaction, and we're going to try to see if we could find another compound that appears only once in the 3 given reactions. So let's start with C2H6. And you'll notice C2H6 only appears in the second reaction, which is great. So we're going to go with it. And so if you remember, the next step is to manipulate that second reaction to match the coefficient and to match the location. So notice that in our desired reaction, C2H6 has a coefficient of 1, and it's on the right side of the arrow. If you have a look at the C2H6 in the second chemical reaction that's given, it has a coefficient of 2 in front, and it's on the left side of the arrow. So we have to manipulate that second equation, and here's how we do it. Well, what we could do is, if you see what happened, I'll talk about it really slowly here, is that notice first of all that we flip the reaction around. We flip the reaction around so that the C2H6 went on the right side of the arrow, just like in the desired reaction. Also, we divided the whole equation by 2 so that the coefficient became 1 in front of the C2H6. So we flip the reaction, which caused the enthalpy change to switch signs. That's why the enthalpy change is positive. Also, we divide the enthalpy change by 2 because we divided the whole equation by 2. So the new enthalpy change of that second equation is 780 kilojoules, positive 780 kilojoules. Right there, you see? So take a second, digest that. And I'm putting now a green check mark in the second equation because, well, C2H6 only appears in that one, and we've confirmed that it has the proper coefficient in front, and it's got the proper location. It's on the right side of the arrow. What do we do next? Desired reaction, it's on the left side of the arrow and has a coefficient of 1. In the third equation that we're given, the H2 is on the left side of the arrow. That's great for us. But the coefficient is 2. So what do we need to do? How do we modify that third equation to make sure the coefficients match? Well, we could just divide by 2. If we divide the entire third equation by 2, the enthalpy change also gets divided by 2. And what that does is that matches now. Oh, I made a little mistake. All right, so what do we do next? Well, we look at a desired reaction, and since we haven't touched H2 yet, we're going to now look at H2. We're going to see, is H2, or does it only appear in one of the reactions that we were given? Remembering again that we cannot touch the first 2 reactions because we have the check mark next to them. They're locked in. So does H2 appear in only one reaction? And yes, it does. It's right there, in the third one. Now we got to check for the location and check for the coefficient. Notice that in our desired reaction, the coefficient is 1 and it's on the left side of the reaction. Notice that the coefficient in the reaction that we're given is 2, but it's also on the left side of the reaction. So the location is good, but the coefficient is wrong. So how do we adjust this? Well, we could divide the third equation by 2. If we divide the third equation by 2, then the enthalpy change gets divided by 2. And now suddenly, to have a look, H2 is in the appropriate location, and it has the same, and it has a good coefficient. So now we get a check mark for the third one. All 3 equations are locked. We have done this step as many times as we can, and we've locked all 3 equations in. Since we've locked all 3 equations in, all we have to do is add the 3 reactions, and we should get our desired reaction. So here's how you add it. Okay, so have a look here. Notice that, let's start with the purple ones. Notice that CO2, there's 2 CO2s on the right side of the top reaction, and there's two CO2s on the left side of the second reaction, and they're both in the gas phase. So since the coefficients are the same, they're in the same phase, they're on the opposite sides of the arrow, those cross out. Next, let's focus on the blue arrows. Notice that in the second reaction, there are 3 water molecules in the liquid state, and then in the third reaction, there's 1 molecule of water in the liquid state on the right side, and there's 2 molecules of water in the liquid state on the right side in the first equation. So that's a total of 3 on the left side and a 3 on the right side. So those will all cross off together. Finally, notice that there are 3 oxygen molecules on the left side on the first reaction, and 1/2 oxygen molecules on the left side in the third chemical reaction. That's 3.5 total on the left side, and there's 3.5 on the right side in the second equation, so those will cross off as well. So we're left with C2H4 and H2, which are on the left side of the arrow, and C2H6, which is on the right side of the arrow, which is exactly what we want to get. So that proves to us, yes, we did everything right. We got the chemical equation that we wanted. If you didn't get it, then you know you made a mistake somewhere. And so, because we have the right reaction, all you have to do to get the enthalpy change is add the enthalpy change of all the reactions. So if you do the math, you'll get about negative 774 kilojoules. So we just figured out what the enthalpy change for our reaction was. And that is all